All right, what I want to do today is get started with Sturm-Liouville equation. So, any general second order differential equation has some coefficient second derivative. This is a very general form of second order differential equation. You've got second derivative, first derivative, y, and something. I'll tell you why we're writing it like this. A Sturm-Liouville differential equation is something where the coefficient Rx, for this, the coefficient Rx is nothing but equal to P prime x. That's the case for Legendre differential equation. Not all second order differential equations satisfy that. If R of x equal to P prime x, that's called a Sturm-Liouville equation. The importance of Sturm-Liouville equation is the following. Of course, I can write, as you know that, I can always write this in the following form. Okay, in the Sturm-Liouville form, I'm also identifying a term like this. Okay, I mean, whatever differential equation is, I want to write it like an eigenvalue equation. Where L operator, here we have gone through this before, is minus P of x, d square over dx square. It's an operator, right? Minus R of x. That is, I mean, I'm just taking it because I want this to be positive, the eigenvalue to be positive. Okay, so I'm writing it in this form. So L operating on y is giving you this part, okay? And that part of the differential equation I'm writing like an eigenvalue part, okay? So this is just an operator. But if this condition Rx equal to P prime x is satisfied for a differential equation, as in Legendre polynomial, then we can say that L is a Hermitian operator. So we are going to sort of connect with some of the matrix, linear algebra kind of a thing. So L becomes, this operator becomes a Hermitian operator
This eigenvalue thing isn't connected with this the condition.
Huh?
This eigenvalue thing isn't connected with that condition. It is still rather there, but if that's satisfied, then L becomes Hermitian.
If it satisfies this condition, on top of it, I'm going to tell you a few more things. There are some conditions to be satisfied, okay? Especially if L is not,
Linear operator.
L is not satisfying that, there are ways to convert that into, we can put a differential equation which doesn't satisfy this, right? We can put it in a Sturm-Liouville form by multiplying by some integrating factor. Then the whole advantage of that is that L becomes Hermitian. I mean, the operator, you force it to be a Hermitian. What is the advantage of in a matrix linear algebra class? If L, supposing, just think of this as H psi equal to E psi, and H is a Hermitian. Something is a Hermitian operator. So what is the, when you learned linear algebra, what are the important properties that you learned if L is H is L, or what are the operators? Hermitian is operating on something. and gives you something eigenvalues times something, okay? So those are the eigenfunctions, right? Basically that will be an eigenfunction. What is the advantage of it? If you sort of remember your linear algebra, it says something about the eigenvalues, it says something about eigenvectors.
Yeah, it's a sum of trace or
No, the eigenvalues have to be real, right?
Yeah.
The other one is eigenfunctions have to be orthogonal. Okay, so what happens is whole thing is, now once you put your differential equation into Sturm-Liouville form, then I know if this is your solution, like it could be Legendre polynomial, Hermite polynomial, I am able to write the orthogonal property of those solutions automatically. Okay, so that is the advantage, and because there will be integrating factors, in the Legendre polynomial, of course, we know that it satisfies automatically. So we know that p integral of -1 to +1 pmx is 0. In others which are not automatically Legendre polynomial, we have not automatically Sturm-Liouville. We have to convert that into Sturm-Liouville form through something that I'm going to talk about, integrating factor. And once we have that, we multiply the original differential equation by that integrating factor, and then we will write, for the solutions, an orthogonal property from there. Okay, without going through the way we did generating function, you have to find that it was a very complicated process to find the orthogonal property, right? I mean,
that if we are able to convert this in Sturm-Liouville form,
yeah,
then it's necessary that we are able to make those equations which satisfies Rx equal to P dot x, or it's
I'm going to show you. Yeah. We will show for that. We have to force it to become Rx equal to P prime x. Like when there's Hermite, like they don't satisfy.
Otherwise, we will not able to convert them to a Sturm-Liouville form.
It's not the differential equation as is not in Sturm-Liouville form, right? I mean, whether it's Hermite or Legendre, it is not in Sturm. It's only Legendre polynomial, Legendre differential equation which is in Sturm-Liouville form. Most of the differential equation that you will come across is not going to satisfy that property. Then you multiply with this integrating factor and bring it to the Sturm-Liouville form. Then you can say something about the solution.
When we are multiplying, then it satisfies this Rx equal to P dot x.
Yeah. So I'm going to prove that all these. I'm just giving you. I mean, it's so why we are. What is the importance of this Sturm-Liouville differential equation is, we are able to get the orthogonal property very easily. Okay, and there will be a weight factor, and the weight factor will be this rho. The normal eigenvalue equation will be like this, right? I mean, you will have h lambda, what h psi equal to e psi kind of a thing. There's a weight factor here, right? I mean, or lambda psi if you want to say. I mean, that's your eigenvalue, right? But here I have a weight factor. So when you write, this is defined, let's say, I mean, you can write, if this is in some regime, then I am going to be, if it is like that, we can maybe it is orthogonal. Okay, I mean, but now we have a weight factor, so you will have supposing you had it like this, so it's called a generalized eigenvalue equation. There's a weight factor times this, it will satisfy an orthogonal relationship like this, and our goal is to find what this rho factor is and all that stuff for each differential equation. Okay, so for each specific differential equation, you will have an orthogonal relationship for your eigenfunctions, okay, with the weighted factor, and so that will be it. Our goal is to somehow find out what that integrating factor is for any differential equation, and you are immediately able to write this, orthogonal property for the solution of the differential equation. That's the importance of this whole thing. Okay. So I'm just giving you we'll just do it within the context of a problem and all that, so then it becomes clearer. All right. Okay, there's one more thing which I wanted to tell you, that not only this, we can prove that L is Hermitian for Sturm-Liouville equation. Okay, that's another thing you need to say this. important. Okay, that's a very general second order differential equation. If Rx equal to P prime X, then we call it, whatever differential equation comes out, we call it a Sturm-Liouville differential equation. So, which is something I can write the differential equation as Px y prime So all I've done is collapse those two things into one, okay? So any differential equation which can be written in this form is called Sturm-Liouville differential equation. And the L operator of the Sturm-Liouville differential equation, so L operator here is very specific, right? Because this is it is P prime. So the L operator of Sturm-Liouville equation will be Hermitian I'll prove it to you also, okay? If it satisfies following certain boundary condition, it satisfies the following boundary condition, yi x p of x yj conjugate of x between a and b is 0. So it's some boundary condition. If this condition is satisfied, where yi is nothing but L operating on yi, it will be hn or pn or whatever it is lambda rho yi. L operating on yj is nothing but lambda rho yj. It's like an eigenvalue equation. Yn and yj are two different eigenfunctions of that operator, okay? In terms of Legendre polynomial or something, if you want to think of it, it is Pn, Px, Pn, Pm, different Legendre polynomials. They don't belong to the same quantum number, basically. Okay. So this is what I mean by yi. Okay. This is what I mean by yj. Okay. So that's so that condition has to be satisfied, and we'll see. We'll be using this also in Green's function method later on. Okay. So in a way, they're all connect. We'll exploit this kind of solving inhomogeneous differential equation satisfying this kind of boundary condition. Now there are various. There's a p prime, I think yj pre. One of them is a derivative. Sorry, this one is the first derivative. So there are different ways of doing this. It could be it could be this. Okay, let me just write down. There are different ways. All of them mean the same thing. I could write it like this. The boundary condition could be this. One of them is derivative between a and b is 0. The other one is conjugate of that, basically. So it could be yj star they mean the same. Okay, there are various ways of satisfying this. One is the solution, whatever solution you're trying to get at x equal to a is 0 or x equal to b is 0, one of them. Or if this is, the other one will be yj prime at b equal to 0. You can have different ways of satisfying this boundary condition. We're not limited. Both can be 0. It is 0 at both upper and lower limits. It's 0 anyway. and you can have P of A equal to 0 or P at B equal to 0. All these things can help you satisfy this. Looks complicated, but there's nothing but you're solving this differential equation subject to certain boundary condition with y, the solution at x equal to, this we are solving in some domain. So the solution at x equal to A should be 0. Solution at B could be 0, that's one type of boundary condition, or you can have the solution at x equal to A, but the first derivative at x equal to B is 0. So this combination of these three terms can be satisfied differently. Okay, so given a problem, if those things are, you look at the boundary condition and say, okay, this operator L is Hermitian for me, and I can use those properties. Okay, we'll apply this, exploit this and we solve the inhomogeneous differential equation. So just pay attention to this, and we'll prove this also. Okay. All right. So basically, we are trying to solve the solution differential equation now subject to a boundary condition. So far, we were not talking about solving differential equation subject to a boundary condition, but now we are going to solve this subject to the fact that the solution at the extremities are 0, or one of the solution is at 0, but the first and also the first derivative is 0, right? I mean, the way to satisfy this. Okay. Okay. So. All right, so all these things are there, and let's I'll try to prove this to you, why this condition is important, and that's what makes it operator L Hermitian, otherwise it is not Hermitian. So I'm going to talk about it. All right. So if we multiplied, so we also write down this otherwise. So the integrating factor is defined as the following. It's exponential of the amount the second term really deviates from the first derivative, okay, divided by the first term. So this is called as integrating factor for the differential equation, and if you multiplied the general second order differential equation, where here at this point Rx is not P prime x, okay? But if you multiply by the integrating factor, this equation should become Px y double prime f times Px. If you multiply f, this becomes, it will be the first derivative of that. So basically, after multiplying by f, we can combine those two terms, and it will be in the term level. That's what this one says, okay? Let's try to understand why it is true, what it is trying to do. All right, so if I multiply by f, I have this equation, right? As simple as this. f of x, p of x, y double prime, plus f of x, r of x, y prime, plus f of x, q of x, y, plus lambda rho of x, f of x, y equal to 0. So this, I just, let's see what I'm going to write. This is what I want, and I'm just claiming that if I multiply it by the original differential equation by that, I can write the first two terms like this, plus f of x, q of x, y plus lambda rho of x, f of x times y equal to 0. Okay, so this is what I'm trying to claim, that if this stuff, if I multiply it to my original differential equation, I should be able to collapse into that. Okay, I mean, let's try to understand what is this. What is this term? The derivative of this is what? F prime of x, p of x, y prime, that's the first term, plus the rest is the same. Now, one thing is you have to understand what is f prime of x. If this is f, my integrating factor, what is f prime of x? Because I have an f prime here, right? So what is, this is my integrating factor, so what is f prime of x?
It's the same multiplied by the...
Multiply by what?
Differentiation of this, which is pu by square x. It's the same, this thing, I think.
So can I write this as exponential of
this.
f of x? Something you integrate and you get function of x, right? I mean, so then if you think of that, then it's easier to understand, right? I mean, then this is nothing but exponential of f of x times f prime of x, okay? So for me, f of x is that quantity, right? Something like this. So what is this? That is my f, right? It gives me back f. And what is this?
F dash x.
Simply r of x minus p prime of x over p of x, right? So this is f prime of x. So that's all you have to understand. The rest is simple. Okay, so that is the integrating factor. And the way to remember the integrating, what it is we want to make that as p prime, right? So I want to see what is the original differential equation, how much it deviates from p prime, okay? And then you sort of normalize it by that factor p of x. The other thing, when you're talking about Sturm Liouville differential equation, don't get confused with our second canonical form of second order differential equation, because there we call p of x as what? The coefficient of y prime divided by this, okay? So p of x is just like a2x or something like that, so in this formula. So don't make that mistake. It is just, in this formula, it is just the coefficient of the second derivative. So it is a2x, a1x, if you call it like that, a0x, it is that. So if you start doing, because you're using the same notation, you'll make a mistake in getting the integrating factor. All right, so once you know that, just now just plug it in and you can see it becomes what I want. So f prime of x is that.
Then f dash x goes to 0.
What goes to 0?
Oh, but here we take that not equal to 0. Sorry, not equal to this Rx not equal to p dash.
Yeah, maybe, very generally we are solving it. So f prime of x, we just substitute there. So in this equation, so all I have is, yeah, do you have some question?
Yeah.
Yeah. So, yeah, okay, so all I have is f of x, r of x minus p prime of x. Okay, p of x is in the denominator and that p of x will cancel. So I have it like that, plus f of x, p prime of x, y prime, plus all those terms, f of x, p of x, y double prime, plus f of x, q of x, y, plus lambda rho of x. The rest is the same, okay? F of x, y equal to 0. Okay. So this term, so I need to recover that. I mean, I have that term, right? So I have that. These terms, of course, have not changed, so I have it exactly the same. Now, what happens to this? We have f of x, r of x, y prime is there, and p prime, that one will get cancelled with that one. So this is really effectively, these three terms will become just one term, which is f of x, rx times y prime. Okay. If you want to now, which is what I wanted, right? I mean, I needed that. So I multiplied by that, and as I just said, if f had that form, I can collapse it into this form, and then I'm trying to justify these two are indeed the same. Okay, that's all I'm trying to do. All right, is it clear? So this is my original differential equation where Rx was not equal to p prime x, and we are claiming that if I multiplied this original differential equation by this quantity, okay, then that's what will become, right? But that equation can be collapsed into this form, and I'm just now trying to, I'm now going back and saying, okay, if that is the case, what is happening? And I'm trying to justify this is what it is, okay? I mean, and everything is, buried in this f prime x, basically, right? I mean, f prime x gives you that. The way they've concocted this term is because, unless you have this form of f prime x, you will not, be able to cancel those terms, right? So yeah, okay. So that's the basis for how to convert any second order differential equation, which is not like even Bessel equation. It's not in Sturm-Liouville form, right? I mean, if you want to do it, you have to find what the integrating factor for that differential equation must be to convert to Sturm-Liouville form, and then in that case, then you can also immediately write what is the orthogonal function, orthogonal relationship, or Jnx, Jmx, because the only difference is I had to find out what is the weight factor for that differential equation, okay, which will come by whatever you're going to be. I will illustrate it, becomes clearer then. All right, is this now clear? Okay. All right. So is it in stem level form? No, right? Because the coefficient of is not the derivative of that, okay? So we want to convert this into stem level form. So we have to find out what is the integrating factor. And let's also define what is P of x in this case, what is R of x in this case, and what is Q of x in this case, and what is lambda in this case.
Px is 1.
Px is 1, okay.
Then what is the Rx? Rx is 2x, minus 2x.
Okay.
And then Qx is 2 alpha.
See, this is where I want you to
Okay,
indicate for
okay.
that. I want you, okay, when we want to do the sum level form, the whole thing is I want to write L operating on Y to
Okay.
be equal to, I want the eigenvalue equation, okay? I mean, everything is based on that, right? And eventually, so I will put Q equal to 0, although it's multiplying Y, but because I want this form, so I will put Q equal to 0. That's what I wrote it. I mean, and alpha is
The
lambda is 2 alpha. Okay, so I just want you to be aware of that. I mean, because the whole idea is to write this operator in this form also. Okay. Okay. So
So
yeah, it's important to understand. Okay. I mean,
why,
yeah.
so why not choose lambda be 0?
No, because I want eigenvalue equation. I want, you know, the whole thing is I'm going to write the orthogonal relationship. I want to write the eigenvalue equation like that. Okay. Lambda rho or lambda if you want to put also rho here. In case it's not, I want. I don't want to put lambda because it's 0 because I don't have it. Okay. I mean, I want to exploit the fact that y has to be orthonormal because the whole idea for me is to get the orthonormal property of my solution without doing it. So I have to write in this form for using this term level, you know, methodology. Okay, so I don't want to put lambda equal to 0. If there is a term under y term, there may be a differential equation where you have, yes, put q equal to, it's up to you to put whatever in the q and, you know, you can do
But
that.
we can take
What?
then lambda is equals to 1 and then rho x equal to something.
No, rho, I'll tell you, will come from the integrating factor. I don't want you to think about what is rho at this point, but that is what will come after I multiply by the integrating factor,
So
okay?
we here didn't talk about rho x,
Hmm?
but usually if we consider this rho x is equals to 1, but we will not consider here.
No. Wait for a minute,
Okay.
it'll become obvious because what I'm trying, whatever it is, here, my L operator is going to change, right? My L operator here is what? D square over dx square, right? Minus 2x, it'll become plus, right? If I'm going to make it plus 2x dx, because I have to write it in this form. I want this also to be positive always, okay? So I want to say 2 alpha y is negative of all that. So this is your L operator at this point, okay? So this L operating, this equation is this actually. Ly is equal to 2 alpha y. Where L is this for my differential equation. That's all I'm trying to say at this point. Okay. Okay, f is then exponential of what? This is okay. R of u, R is negative 2u. That is 0. P is 1. Okay. Times. Okay. This. So my integrating factor is this. So if I multiply by exponential of minus x squared, this equation becomes my original Hermite differential equation is then exponential of minus x squared y double prime minus 2x exponential of plus 2 alpha x squared. Okay, so this is the one which I can club it into one of them. Which will I can write it as d over dx of exponential x squared y prime, right? I mean, so this is just a differential, right? I mean, now because the way it is, we write it right. Kind of a thing, right? I mean, so it's a differential of can I combine it, the first two terms? That is the first term, and that is the second term. So this term, now this is in the Sturm-Liouville form. Okay, it is the Sturm-Liouville form. Once it is there, is when we can write the alpha. Now you see the rho here. Okay, so that is your lambda. This is your rho factor here. So the eigenvalue, we know this is this solution, Hn, let's say Hermite polynomial, Hn and Hm are solutions of this differential equation, and you can solve, by the usual method. You know what Hn and Hm are. Then, and if this is being defined in the infinite domain, then I have the orthogonal property is nothing but, without any generating function method or anything, I can just write I can put the weight factor here, and so this will be for n not equal to m, the Hermite polynomials have to satisfy this particular orthogonal property. Okay, so this will be the orthogonal property for because the original Hermite, the differential equation, it does not satisfy. In Legendre polynomial, we could do this, right? I mean, we could do that without any weight factor, right? That was for n not equal to m, because it automatically satisfied Legendre differential, the Sturm-Liouville form. Whereas this one did not satisfy. I had to multiply by exponential negative x squared to bring it in this Sturm-Liouville form. Okay, this is now in the Sturm-Liouville form. Then I have, now you can see lambda rho y kind of form is there. So once you put this, you identify in this differential equation what is your rho. Okay, so this is your lambda, which we know. So this is your lambda, and this is your rho. Okay, so you have gone to this kind of a differential equation now. Ly is equal to lambda rho y. So there's a weight factor here. So it's a more like a generalized eigenvalue equation. In a generalized eigenvalue equation, it's not integral of ynx, ymx is equal to 0. It is rho times ynx, ymx in that whatever domain you're defining becomes 0. And what is this? Is going to be different. This weight factor is going to be different for different types of differential equation. Okay, I mean, Hermite it is this. Bessel it will be different, and Laguerre will do, because that's another thing you may come across. It'll be a different weight factor. You must be wondering why, orthogonal property has this kind of different things in different special function. That's all because the original differential equation, if it was not in Sturm-Liouville form, unlike Legendre polynomial, there will be some factor in the orthogonal property of the Legendre form, the corresponding, solution of your differential equation. Okay, that's all. So you will see this all the time. There will be some weight factors. Okay, I mean,
your QX remains 0. Now it.
Yeah. QX still is 0. Yeah, it has. Yeah. The whole idea is QX is not so important. I want to combine. Those factors are important. Okay. So this is your rho here. do you now understand how to identify rho? And the whole problem is you have to identify your px, qx, and rx. Qx, what is qx and what is lambda, because that will be the confusion whether should I put it as an eigenvalue or qx. But remember that I need to have the eigenvalue, because whole idea of the premise on which this whole method is you're converting somehow the original differential equation into an eigenvalue type of problem. You're completely reframing the problem, right? So you're converting into eigenvalue kind of a problem, and then trying to say, okay, then I know this is my, if L is Hermitian, which I'm going to prove. If L is Hermitian, then eigenvectors have to be orthonormal, and and more than that, if the eigenvalue equation, not the typical eigenvalue equation, but if your weight factor is there, like this, then that will be the orthonormal property. You must have rho of x, ynx, ymx equal to 0. Okay, and what is so the whole idea is what is rho of x for your differential equation. That's all you have to identify. Okay, so the orthonormal property is whatever regime you're looking at will be rho of x, y and x, maybe conjugate, also if it is a complex number, it will be something like this. All right. So our goal is to identify this after converting the differential equation into this term derivative form. What is rho, and is an important thing for you to understand. That's all we're trying to do.
This is somehow represents the boundary condition also. No, not this.
What did you say?
Boundary condition.
I'm going to talk about that in a minute. The boundary condition, how to I have to derive the whole thing. What I'm going to do is the following, right? The whole premise of the whole thing is the following. I'm going to use this method eventually for inhomogeneous differential equation. I will write it in this form, okay? And of course you can solve the problem only if L is Hermitian. Then it has to satisfy certain boundary conditions and stuff like that. Okay. All right. Some version of it will come in hydrogen atom problem. It will be associated Laguerre, but there'll be a few terms slightly different, but we'll come across this. Okay, is it in Sturm Liouville? Is it a Sturm Liouville differential equation? No. All right. So convert that into Sturm Liouville form.
Multiply by x.
Okay, so what is P of x?
X.
Okay, R of x?
1 minus x. Q of x is 0.
Yeah.
Lambda is n.
Yeah. All right. Fine. So what is your integrating factor then? Exponential of Rx, right? Ru minus deviation from whatever that P of u, D of u, x. So this is
Negative x.
okay. So that is what R of u is 1 minus u prime of u is minus 1. P of u is u. Okay, so 1, 1 is 1 is 0.
Negative
So
1.
it is negative du, right? So it is exponential of negative x. The weight factor, the integrating factor is this. For negative is. So what you're trying to say is if you multiply by exponential of x, all right? So right, that is the first term, right? And then this should develop into two terms, right? I mean, so basically you have to verify really it has become that, right? I mean, so that will be the Sturm Liouville form because I want this term to be the first derivative of, this quantity, right? And so that, basically that should give you the second term. The first term is obvious, I mean, yeah. Okay, so what is the weight factor here now? The
e to the power.
minus x. So this is your rho. So basically your L operator now is this, right? I mean, without, So L operator is d over dx of all these things. So this is your L operator. Plus. You can make this sign perhaps, and then then we can put it this as positive you want to keep. So that is your L operator, and so the weight factor is exponential of minus x. If Ln and MLm are Laguerre polynomials of order n and m, and let's say this is in the region 0 to infinity. We're solving this in this regime. So what should I put here?
E to the power
Minus x, okay. So you will see this kind of a thing that in orthogonal property, this weight factor changing from one special function to another, and that's because of the integrating factor and what that leads to in terms of rho. Okay, so that is the reason why for Legendre polynomial, since it's automatically in the SL form, Sturm Liouville form, this weight factor rho is 1. In other cases, the weight factor can change, whatever it is. It will depend on the. I think I have a feeling the Bessel function is rho or something like that. It is not exponential, something else. We'll you can work it out. Yeah. So I did this because you will see these orthogonal property and you may be wondering where these things are coming from. All they're trying to do is convert the original differential equation into the Sturm Liouville form. Okay, that's all they're trying to do. All right. Okay, so we are trying to solve some problem. Okay, where lambda y or lambda rho y, depending on what equation. Okay. And we are trying to solve this in this so what I want to prove right now is L is Hermitian if these conditions are satisfied. Okay, so this is an important criteria. Okay, so I'm going to recall from quantum mechanics basically. Now for an operator to be Hermitian, we know that yi and yj are two eigenfunctions of this operator L. Y of x, p of x, y of x, L operating on yjx, the other eigenfunction, dx should be equal to a to b of L operating on yi star yjx dx. Okay. So I have to prove this condition. Let me call this left hand side, let me call this right hand side. This condition has to be solved. This is a, for any operator to be Hermitian, this is a condition it has to satisfy. Because L dagger is L, that is sort of taken into account. Definition of the operator to be Hermitian is taken into account, and that's why you can do this. Otherwise, you cannot do that. Okay, so it is so L dagger has to be L. I mean transport, and the conjugate thing. But so here I'm just taking the conjugate. Okay, so that's enough. So this is what we have to prove. Okay, so if the L operator satisfies, then L is Hermitian. And what I'm going to say is that this is possible only if this condition is satisfied. That's what that's where the boundary condition come from. Okay, so we have to prove all these things. Let me write on this clearly because that's the important thing. All right, now let's this is true, the conjugate of that is also true. We may need that condition also. We will just prove it in a way. We'll see what all condition it has to satisfy. So I'm assuming L to be already in your Sturm Liouville operator. All right. L operating on Y is lambda rho of Y. L operating on Yj is lambda rho of Yj. Okay. Where L is what? I'm saying it is a Sturm Liouville operator. So how should I write it for a? If L is Sturm Liouville operator, can I write this as negative p of x? L is Sturm Liouville, so I'm writing this as negative minus px y prime and take the derivative of that. That's what we were trying to do, right? I mean, that's what we mean by Sturm Liouville form. So this is Sturm Liouville operator. So that means this is what I can do for it. All right. So what do I have to do? I have yi prime operating on Lyj. So this whole thing is L operator. Okay. So L operator also has qx. So we have to do all that. So I need to, let's look at the left hand side only. Okay. Left hand side is then integral a to b of all these things. Okay. Yi conjugate. And I have to take all these things, negative p of x, yj prime of x, and I have to take the derivative of that, and I have another term, actually there are two terms, minus a to b of yi conjugate of x, is it plus or minus qx? Oops, yeah, it is this. Okay. Minus yi prime q of x yjx dx equal to the right hand side. I have to remember that a to b of l y I conjugate of that yjx dx. All right. I'm going to integrate the first term by parts, which I can do, right? I mean, I got this. So the whole idea is, putting in this form, integration becomes easier. Integrate the first term by parts. All right, so that will give me the following stuff. Replace all these things. All right, what I will get is the following. Yi star, complex conjugate, x, negative p of x, first derivative of yj, okay, that is the first term. I integrate that, and the other one I take it as such, and I have to evaluate this between a and b, and then I can have one more term, right? Negative of something, and then that becomes positive because of the two negative sign, and I have to take the derivative of that term. Yi conjugate x, I have to take the derivative, and then p of x, this term I have to keep it as is, right? And I have to evaluate this between A and B. And I do have that term also, minus A to B yi star of x yjx dx. So what I'm writing is the left-hand side only that part, and I have to show that is equal to that. Okay, so one of the conditions you can see why I need to, this is where, okay, this is derivative, but you prove it, you can catch it. So this has to be 0, so that's where the condition comes from. But still I have to prove that is equal to left hand side, doesn't happen, I have to do one more thing. So this is 0, this is the boundary condition. For it to be Hermitian, to prove that, I need to make that go to 0. Okay, I need to take the derivative one more time. Let's see, I got this, right, term. What I'm going to do is, this term I'm going to take the derivative of that term and see what happens. So do integration by parts one more time of the left hand side.
Of both the terms?
Only this term, okay. So if I take that first derivative, so I do get what? So this term, right, left hand side effectively is becoming yjx, okay, and I have p of x, yi
Yix.
conjugate of that, and the derivative of that x, okay. That is what we need to evaluate a and b, negative of a to b. Now this time I have to take the derivative of this whole term, right? So I have p of x yi star conjugate of this. I have to take again the derivative of that, just integration by parts, okay? And since I already integrated other one, this is yjx dx, and other term I can put it the same way. Minus a to b of yi conjugate of x q of x yjx dx equal to this left hand. I need to prove this, right? It is equal to that. That's what I need to do. All right. So this is what I have. So this is, this term has become split into those two terms, and that is that term. Okay. Now, if I make, it looks like that, right? It is really the conjugate of yeah, it is. Yeah, it is. Yeah. So I also have to win. Both conditions have to be satisfied. But they really mean the same thing. Yi. So basically, there are various ways to satisfy the solution. Y and yj are solutions of the original differential equation. So they have to be 0, right, at the extremities, or the derivative of that solution have to be 0, or So if that is 0, they are very similar boundary condition. Then I end up with that. Okay. Now, is this term same as that? That's what you have to verify.
from the Sturm-Liouville equation.
Yeah, so L is, we had it, right? I mean, so this is nothing but, my right hand side is what? Now, just expand it out. I mean, A to B of, what was that? Minus Px minus Px yi, is it minus Px yi conjugate prime, right? Derivative of that, right? The whole thing, that is L, that yjx, that will be the first term, right? I mean, and then the next term will be minus A to B, that will be the simple term, minus of qx, yi conjugate prime x yjx dx. Is this what we have? Yjx and my f is yx. Okay. All right. Minus of that. Okay, so minus qx. Okay. So you have proved the only way, this is the main condition, right? I mean, for operator to be Hermitian, this condition has to be satisfied. L, we have already put it in the Sturm-Liouville form, operator form, and all we are trying to say is the left-hand side is equal to right-hand side, provided these conditions are satisfied. That's all it is. So we have to have whatever solution you're trying to satisfy this problem. The solutions have to be such that it vanishes at the extremity. Supposing you're solving yi at A equal to B, it has to be 0, or yj at B equal to 0, or conjugate of that, doesn't matter, right? I mean, the original or conjugate doesn't matter. Or we can have other things also, or the way the boundary conditions are different types. Either also the derivatives can also satisfy this way also yi, but the derivative of the solution at B equal to 0, there are various ways of satisfying it. Okay, so it's a little bit more general than what we think. Okay, so yes, so in a way, Sturm-Liouville equation is a differential equation you're solving subject to some boundary conditions. Okay, so that's what it is. And we will use this in Green's function method. We are going to use this approach.
By integrating factor, we can obtain all means all the equations from Sturm-Liouville equation.
Yeah. Yeah, you can use the integrating factor, yes.
And then we can obtain all the equation, all the second order differential equation from this.
You can, it is used, yeah, it is useful only for getting, in some sense, the orthogonal property of your solution. But I'm going to exploit this the two things I'll exploit next time are linearity and the fact that it's a Hermitian operator. How can I use that for such differential equations? I'm going to give a method for solving inhomogeneous differential equations. So far, we have been considering only homogeneous differential equations. Okay, so there are two different ways of solving inhomogeneous differential equation. One is called eigenfunction method. From the eigenfunction, set up what's called Green's function and then get the solution. Okay, so that's the reason why I went through it, because you may not understand why this strange boundary condition looks very, very strange otherwise, right? I mean, but that is needed for what I'm going to cover. So I just want you to have at least have an idea where they're coming from, because I want the operator L to be Hermitian. Okay, the Sturm-Liouville operator, but in order for the Sturm-Liouville operator to be Hermitian, we have another condition. That's the important thing. Okay, there are two things. So I need my L operator to be Hermitian for solving the inhomogeneous eigenfunction, inhomogeneous differential equation using eigenfunction method. There's another method which doesn't depend on that. Okay, it could be for any operator. But if I want to exploit that, in some sense we're converting the differential equation problem to an eigenvalue kind of a problem, right? We just completely now change the language, right? I mean, Yeah, just the differential operator I'm calling, okay, it's a differential operator, and I'm writing like an eigenvalue equation, okay. So it's completely slowly trying to change the methodology of solving homogeneous and inhomogeneous differential equations. That's an under approach, right? I mean, we are not using power series method or something. It's a completely different approach. So I just want you to be, so I just want to have an appreciation for it, but where it's coming from, because otherwise it looks like a very funny, strange boundary condition. But so all it says is the solution, whatever solutions are, either the solution itself vanishes at both the boundary condition, or the solution, one of the solution can vanish at the boundary condition, and the derivative could also vanish at the boundary condition. That's all it says. Okay, I mean, so there are various ways of satisfying. Even PA and PB could be 0. Even if Y is not, of course, that condition can also be satisfied if there is an equation for which this is satisfied. L could be Hermitian. Okay, so that's all it is. So it looks very bad, but it is not. It's not. There are various ways of satisfying this. First one, the solution starts, the derivative goes to 0, and the second solution, at b equal to 0. I mean, these are the different ways. At least these are different combinations by which we can satisfy this condition. Okay. All right. Okay. Let me stop here today.
We will meet next Tuesday.
We are after the fall break. We meet on
Thursday.
Not Thursday. Thursday we are not the class.
Next week. Next to next week.
Yeah. And on October 12th, since there's no class, but there's a bullet lecture that evening at 7 p.m. So maybe you